on today's session is a bipolar junction transistor BJT. Now you have other type of transistor like field effect transistor, which is called FET. So once you study the BJT, in the future, if you come across other type of transistors like MOSFET, FET, and so on, so you would have a good grounding to understand other type of transistors. Now, as you can see on the diagram here, a bipolar junction transistor is composed of two PN junctions. Remember, we started this module with the topic of PN junctions. So we've quite understood well how a PN junction works, a diode in a way works. We studied the normal diode, the Zener diode. So one of these elements there is one PN junction. Yep. So it means we are now sticking together three wafers, if you want, three semiconductors, and two of them are the same type. So it has a P and P. So you do have another option now is to have an NPN. So we'll understand the difference in a few minutes. Since you have these two options to create two PN junctions, so you can PNP or NPN, you have two types of transistors, two types of bipolar transistors. One is called PNP transistor, the second one is called NPN transistor, simply because it depends on the number of regions you're creating of P and N type. Okay. Now, let's try to see in terms of distribution. So I'll be sending out these notes to you. I'm going to cover the main important topics. Yeah, and then when you're reading them, if you have any doubts, you can come back in the intro session or by email or of online sessions. You can correct those doubts. Now, if you see on the two diagrams there are three letters given. It's E there, and then B, and then C. The same thing here, E, B, C. So the E stands for emitter, the B for base, and C collector. So in a bipolar junction transistor, you will always have three regions or three terminals called emitter, base, and collector. Now the name itself says a lot. Emitter is a source of charge, okay? And C is collector. It's like charge would always flow from the emitter to the collector, and the role of a base will become clear as we go along. Yeah? So a very small amount of charge would actually go to the base, but most of the charges would flow from the emitter to the collector, be it the PNP or NPN. So in both cases, you find that the terminal on the left is always emitter. So be it the PNP type or NPN type, we always have an emitter being the source of charge, and the collector is like receiving this charge. Okay, and you have the base there. As I said, it will become clearer later what happens. Now let's take the PNP transistor to start off. We know the P type would have the positive majority charge carriers. As we said earlier, the N would have the minority charge carriers. The negative sign. The negative is electrons as majority charge carriers, and again P is same. Okay, we do have minority carriers in both cases. We've explained that why is present there. So we always have some minority carriers, but the main flow of charge would always be due to the majority charge carriers. Now, if you take this case there of, let me see the emitters there. So it means we want charge to flow from this region there to that side. Now, in terms of number of charges, you find that in the base there, which is the N here, you find less number of carriers. So if I just want to show you what's the reason for that, there's another document I've created for you. It's a PowerPoint slide. So I'll be using both of them as go along. So if you look at this one now, yeah, this one. So here you see a bit in more detail the relative sizes of these three regions. In the diagram just shown to you, all three were shown to be of equal size. It's not the case. When the PNP transistor or NPN transistor is constructed, you find that the emitter and the collector are quite large relative to the base. So the base is quite small if you consider the dimensions given there. So this one is 0.150 inch, and this one, the base is very small. So this is the reason why the amount of charges shown on the base is very less. Be it in the PNP or NPN, against the P region there is again very small. Okay, so I'm going to shift back to the handout. But every now and then I'll be shifting to this PowerPoint slide just to clarify. Okay. So I hope it is clear now why, in terms of region, in terms of charge carriers, the majority charge carriers, you have less in the base. Okay. Now let's just see. Let's consider now you want to send charge from the P here, which is the emitter, to this side. You would have to connect here a positive sign to push this charge, because you want to make the charge flow from the emitter to the collector. Pay attention to this very well, because soon we'll not be using this type of distribution of charge. We're going to come to a symbol for the transistor. Yeah, but then if you understand very well what I'm explaining now, it becomes clear what that symbol is. You'll be able to see through the symbol in a way. Okay, so like we said, this region there is called the emitter. and you want to send the charge from the emitter to the collector. So in this case, since the P for the emitter, you would want to send this positive charge, which is a majority charge carriers, to the collector. How can you do that? You would have to connect positive on this side, and you would have to connect a negative on this side to attract the positive. So you want to have a net flow. So for biasing, so this is what's called about the name. Biasing means you have to correctly connect the correct polarity of battery to your emitter and your collector and your base as well, to be able to have a net flow of charge from the emitter to the collector. So in this case, since your emitter have positive charges as majority carriers, you would have to connect a positive to sort of push the positive charges on the side, and you would have to have a negative charge there to attract them, to have a constant flow. Now look at what the base is connected. Since you still want to have an overall flow there, it means this has to be positive, and then this one would have to be less positive, so that there's still a flow. So this is why it is grounded. Yep. And then this one would have to be, the collector would have to be more negative than the base for charge to keep flowing. This is a relative, if you want, polarity of the different regions. So definitely for you to have a flow from the emitter to the collector, you would have to push the positive signs from the emitter. So definitely a plus there. And then you would need definitely a negative on this side to attract this negative. And then the base would have to sit between the positive and the negative. In a way, here it's grounded. Okay, so very important. Now there's one mnemonic to remember this. If you want to do the correct biasing, you can come to a diagram like this always. But there's a mnemonic to remember. If you look at the name there, P and P. Yep. So what sits in the middle is N. It means the emitter. Sorry, since you have an N there, it means the collector and the base will have to be more negative than the emitter. The N there is a mnemonic, so it's just a trick for you to remember. But like I said, if you want to redraw this diagram and see the biasing, you can do that. But whenever you get it's a question to solve on transistors, you would always need to check the biasing. And a very good mnemonic and a very good trick to remember is, if you have a P and P transistor, the middle character is N, so the collector and the base have to be more negative than the emitter. This is one mnemonic. Okay. Now, based on that, I will come to symbol in a few minutes. So this is a symbol for PNP. I will explain that in a few minutes. Let's come to the NPN. Okay. So NPN, similar to what you've just done. So in the N region of an emitter, you would have negative now as a majority carriers. Same thing on the collector, because it's NPN. And on the base now, you have the positive signs. So if you want to have a net flow of charge now from the emitter, which is negative, to the collector side, so same kind of logic, but now you agree, you would need to connect a negative sign here to push these negative signs forward, yep, towards the collector, and you will have to have a positive polarity on this side to attract the negative. Yep. And as usual, the base would have to sit between this polarity and this one. So the base in this way would have to be positive, but less positive than the collector, because you would want to have a flow from here to here, but continue the flow from here to here. Yeah. So the collector would be positive, the base would be positive, but less positive than the collector, and the emitter in this case would be negative. Now, why negative? And to repeat that, you would want to push these electrons in the emitter, which is an N-type. So to push the electrons, you have to connect negative. So the negative sign here, the polarity is going to push electrons because electrons are negative. So if you connect a negative, that's going to push it. And then you would have to have a positive here to attract it. Okay. So if you understand these two biasing, so again, the mnemonic comes in. The NPN is NPN. So the P there stands for positive. It means now the collector and the base have to be more positive than the emitter. Yep. So again, for P and P, we found the opposite should be more negative. We've seen the logic behind it, but you can't always come to a diagram to understand it. But you got the logic clear. But like I said, in questions where you need to check the biasing, it's a very good trick, a small mnemonic for you. So if you have an NPN transistor, the collector and the base would have to be more positive than the emitter. So it's always comparison to the emitter. Okay. Now I will shift back to the lecture notes now on PowerPoint to explain the symbols. The symbols are here, fine, but it's easier to explain the logic behind the symbols in the lecture slides. Yeah. I'm shifting to PowerPoint now. So henceforth, we won't be always using the distribution of charges like we've just done. we'll be using these symbols now. No problem with my mouse. Okay. So I hope you can see my slide. Yeah, okay. So we've discussed that already, and you can now understand these polarities. Why is it positive here? So why is it negative? So we just explained that. But this diagram is not showing any charge distribution as such, but we just explained that. So this is more clarity. Now, what do you observe now? Since you're connecting now, so remember this one, for example, is a PN. This is a PNP transistor. Yeah. So can you see that since you're connecting positive here to the P, and you're connecting negative, so positive here on the emitter, and on this side here's a negative. So this junction there is forward biased. Yeah. Can you see that? This is a junction, because since you're P and P, you have two junctions now, two depletion region. So the first depletion region, which is between the emitter and the base, is forward biased because you're connecting positive on this side, and so positive to the anode in a way, and negative to the cathode. But look at this one now. So you have now the P's here and the N is there, yeah, because the P and P transistor. These two are the same transistors, they're not two transistors. So if you consider now how this is connected, so the P is always the anode, but you're connecting a negative sign now to your anode, and a positive sign now to your cathode. So this depletion region, if you want, this barrier here, is actually reverse biased. So you will always have this for both transistors, be it NPN and PNP. For a transistor which is properly biased, the emitter base junction, the first junction, would always be forward biased, and the base collector region, the base collection depletion region, would be reverse biased, as you can see here. Yeah. So this would be common for both transistors. Yeah. So one junction is found to be forward biased. So this one is forward biased because the P is connected to positive, and the N is connected to negative. But if you look at this one now, the positive, the P1 now is connected to negative, and the N1 is connected to positive. So it means it is reverse biased. Okay. Okay, so this one is showing the total both junctions put together. So we'll just look at that. And this one is the P and P transistor. So same, just to recap, you can find P and P. So the N there can be considered to be negative. So this is why now the collector and the base are more negative than the emitter. Yeah, so just remember this. Now, this diagram is interesting. It is also showing the currents. Yeah, because definitely you have a current. Now, the source of charge is always the emitter. And you see IE there is a current which is originating from the emitter. So in all transistors, the relationship always holds that IE, which is the main source current, is equal to IB plus IC. It's Kirchhoff's current law here. So IE is an emitter, so the source of current, and this current there, IE, is split into IB and IC. Yeah, so P and P, one PN, you always have this relationship. That's important, very important relationship. Now let's come to the symbol. So I've just talked about this I is equal to IC plus IB. Now don't be confused now, just take one by one. Let's take this one. Just take P and P, just understand why the symbol looks like this. So if you just look at the symbol, you always have an emitter, the base, the collector. This one as well, emitter, base, and the collector. Let's look at the first one. The first one is P and P. Remember, in terms of charge distribution, this P there had positive charges on it. So the emitter was sending positive charges away from it. So emitter is sending positive charges away from it towards the collector. We very well know that the direction shown for conventional current is a flow of positive charge. By convention, before electrons were discovered, people were thinking that actually current is a flow of positive charge. So since what is flowing in a PNP transistor is actually positive charge, because the emitter is a P region, this is why the arrow is shown along the direction itself. So the emitter is sending positive charge away from it, so the arrow is away from it. You see? So let me just repeat that, very important. For a PNP transistor, the emitter is actually a P-type semiconductor. So it will have positive charges in it, and the emitter is always a source of charge. So what is flowing from the emitter is positive charge. So it means the direction that you would show is actually the correct direction, because positive charge is already flowing away from it. So if you find a symbol for a PNP transistor, you'll find the arrow which is flowing from the emitter towards the base is away from the emitter, because it is already positive charge. On the other hand, when you look at an NPN transistor, the emitter is still a source of charge. The emitter is always a source of charge, but in this case, the emitter is an N-type semiconductor. Yeah, and in the N-type semiconductor, the majority carriers are negative. We do that. We just see that in the distribution. So even if the emitter is sending electrons away from it, we have to reverse the direction now because the direction of current is a flow of positive charge. This is why now for an NPN transistor, you would see the direction of arrow going into the emitter because what is flowing away from it are actually electrons. But you have to reverse the direction to show the direction of positive charges because by convention, current is flow of positive charges. So for an NPN transistor, the arrow would come into the emitter. That's all. Yeah. So I hope it is clear. If not, I can explain again. So henceforth, we won't be finding charges like this or diagrams like this for transistors, even if that's how it looks like. If you look at the transistor, it will be like different regions similar to this one, but on circuit diagrams, we will be using this type of symbols henceforth. Let's look in terms of currents. So this one, you can see the current, the emitter current is going into it. Yeah, because it's the p-type, so it's already the same direction of current. So IE is along the direction of flow of charge because that's a convention for the current. So IE is flowing here, and then it is split into two currents, IB and IC. So this relationship is still holding. So the IE goes in and splits into two currents. Direction is very important here. So IE goes in. So what comes out is IC and IB. So this relationship still holds. Let's look at this one now. Since the NPN transistor is the flow of negative charges because of an N-type, you would reverse direction to the direction of current. This is what you've done here. So since current, what is flowing from the emitter are negative charges. So if you want to show electrons actually flowing in this direction, just like we have seen before, but since we have to reverse the direction to show positive charge, you are now reversing. So the IE is flowing in this direction now, and by Kirchhoff's current law, IB and IC will have to flow in this direction to make up. So now it's like as if IC plus IB is creating IE, whereas this one, IE is creating IB and IC. Yeah. So this relationship holds for both cases. It's just a question of direction. Okay. So if anything is not clear, you stop me. Okay. Now let me shift back to the handout in PDF to continue. Yeah. So I hope now it's clear the two symbols. Very important because this is what we'll be using exclusively now. We won't be using the regions. So now when you read your handouts, it'll be clear why this is a PNP transistor. Yeah, because emitters there sending positive charges, whereas this one is an NPN transistor. So the emitter is still sending charge into these two, but since they are electrons, you will have to reverse direction. So whenever you see the arrow pointing into the emitter is an NPN, and when the arrow is pointing away from the emitter, it will be NPN. Okay, so I hope it's clear. You have to bear that in mind. Now we've already seen all these types of biasing. Yeah, we've already seen this type of biasing. Why this has to be positive? Why this is how to be negative? So and you would have to always identify. But for example, let's take this one. This one is a PNP transistor because you can see the arrow from the emitter is the arrow is away from it. So already positive charge there. Yep. And since a PNP transistor, the collector and the base will have to be more negative. Yeah, the end there is a trick, like I said. So it means indeed the collector is negative and the base is grounded and the emitter is more positive. So in a way, your collector and your base will have to be more negative. If you look at this one here, your PNP transistor, so what sits in the middle is a P. Yeah, so it means the collector and the base will have to be more positive, and this is what you see. The collector and the base are more positive than the emitter, which is on the negative side. Okay. So this is the type of circuits you'll be coming across. Yeah. So we're going to do some calculations on them in a few minutes. These equations always hold. I is going to IB plus IC, like we said in both cases. Now you will see some configurations as we go along. Now this one is called a common base configuration, simply because the base is sitting between the emitter and the collector. As you can see here, the base is in the middle. Yeah. So this is called a common base configuration. But the rule of biasing is the same still. You can see in the middle you have a negative sign. It means the collector and the base have to be more negative. Indeed, they are. Yeah. So we'll be doing some calculations later, and you have to identify a type of configuration. Very easy to identify. Whatever is common here, in this case, your base is common to your, so it's sitting in between if you want. Now, this would be calling the input side, and this one will be referred to as the output side. Okay? And this one is not an input, no an output, it's a common if you want. This one is called a common base. Okay. Now, if you consider this situation there, the input current there is IE, the output current is IC. We always tend to take a ratio of output to input, as we've seen in many cases. So if you take the ratio here of output, which is IC, and the input, which is IE, you get a ratio like this, IC over IE. We call that an alpha. Okay, so alpha is equal to IC over IE. Now, one important factor which I've mentioned at the start of the class is the current IB is a very small current. Very small current, it can be 1 to 2% only of these two currents. So if, for example, you're sending where, let's say 1 ampere, let's say, this one would be almost 1 ampere. This one will be, let's say, 0.002 ampere, something like this. Very small. But if you don't have any IB, no current can flow from the emitter to collector. So in a way, the base there is like it's like an important signal. It is small, yes, but it actually controls the transistor. If you don't have a current in the base, you want the transistor would actually be off. So it's analogous if you want to a relay. You know, a relay is a device which takes a very small current to turn on a switch which controls a much larger current. So it is analogous here to a relay. Yep. So even if the current IB is very small, it is still very important for that small current to flow. Else, because we know the base sits between the emitter and the collector, if the base is itself switched off, then no current can flow from the emitter to the base, and it means current cannot flow from the emitter to the collector. So now, why the base is small? We say that the base current is small because that part of a region is actually a very small region with very small amount of charge. Yeah, this is why it is small, but it needs to have a current. Okay. Now, since the IB current is very small, if you take a ratio of IC over IE, it will be very close to 1 because these two are almost the same. So alpha would typically be very close to 1. It can be 0.97, it can be 0.98. It also means in a question, if you're not given the value of alpha, you can assume it to be 1. Okay, so very important. If in a question given to you, you would need, say you have been able to find IE and you would need to find IC, and alpha is not given, you can assume it to be 1. Yep, this is what I want. Okay, so you can read through all this. There are all the different manipulations there which you can have. Now, this equation, as you find here, is simply coming from the equation I is equal to IB plus IC. So from there, you can say that IB is equal to 1 minus alpha times IE, something like this. Yeah. So this is coming from the fundamental equation we mentioned earlier. This one, I is equal to IB plus IC. So it means you are saying here IB is equal to IE minus IC. And since we've just said that alpha is equal to IC over IE, you can make some manipulation and come to simulations. There's nothing difficult there. You can. Now, next configuration which we look at is a common emitter configuration. So if you look at the common emitter configuration, the biasing would be very same. So I'm not going to cover the biasing again. Now, important now, you have to get used to this. If you look at this transistor there, you can find the arrow is going away from the emitter. This is a PNP transistor. Whereas this one, the arrow is coming into the emitter. It has to be an NPN transistor. Yeah, you have to get used to that. This, if you don't get it clear now on your own, you have to look at the diagram with different charge distribution and then look at the symbol. You should be able to understand why. If not, I can explain it in subsequent session. But when you look at the symbol here, you should know now by default this is a PNP transistor, this one is an NPN transistor. And then once you know that, you would know the biasing straight away. Using the trick I've said. Now, important in this case, a common emitter. Why is it called a common emitter configuration? Simply because the emitter now is sitting between the base and the collector. So in this case, IB, so the base here, IB would be the input current and IC would be the output current. Okay, and IE would not be the input current, nor the output current. It would be just be a common current in between the two. Now, just like we've just done, in that case, if IC is output current and IB is input current, the ratio that you would take is IC over IB, as shown here. So this ratio is called beta now. The alpha was IC over IE. So you would use IC over IE for a common base configuration. And you would use an IC over IB for a common emitter configuration. Now, what can you say about this ratio, IC over IB? Since IB is a very small value, we've said that earlier, this ratio beta will be quite large. It can be 100, it can be 200, depending on the transistor. So you expect this ratio beta to be quite large because IB is a small value. Now, just like we've done earlier, you can do some manipulation. So I would invite you to look at these different relationships here, and you can try to derive now what's a relationship between alpha and beta. Yeah, we've already know that alpha is equal to IC over IE and beta and so on, and we know the relationship that I is equal to IB plus IC. Yep. So now you can start doing some manipulation, and you can find relationships like this. So alpha is equal to beta over 1 plus beta. Yep. So you can now the common collector configuration we won't consider it because it's not very much used. So don't worry about the common collector. You can read about it later if you want. So common collector is not a configuration which is used, which is not used at all. Yep, so we are skipping this one. Leakage current as well, you don't need to worry about it. You would consider leakage current in transistor circuit if you want to be more accurate in terms of modeling a transistor. The leakage current is a very small component of a whole current. If you ignore it, you would still get a reasonable value for your current. So we are not considering, so forget about leakage current. If you want in the future to read about it. So you do have a powerful leakage current, but don't worry about this part there. Yep, so be it a leakage in the common base configuration or common emitter configuration or the other one, don't worry about it. So these examples there, you don't need to worry about it because they are about leakage currents. Okay. Now, test circuits are also not important for you. So test circuits, just to say briefly about it, test circuits are circuits which you would run in the lab to be able to get different characteristic curves for transistors. So you get curves like this for different variations of your, for example, if you are in the common base configuration and you start varying your common base voltage, what would you get in terms of collector current? So it's always like an experimental circuit. So this is not part of your curriculum. You are more on applications of transistors. You would do that, like I've said, if you are following more electrical engineering course. Yeah. So these test circuits, the common emitter, common base is not very important for you. Yeah, so you got the example. Okay, so all this not really. So now let's come to here. This is the important part for you. How do we solve? How do we calculate currents in transistor circuits? Okay, so let's look at this one. We have around 5 minutes left before session ends. Like I said, when it ends, just join in the same session, and we have like one more session, and we should be. Yep. So let's look at how we solve this type of transistor circuits. Now, whenever you get a circuit, first thing you have to identify is to do very straightforward what the base is. The base is always where you have this sort of this bar there. Okay, and the emitter would be always the region where you have the bar with arrow. The arrow can be going into the emitter or away from it. We've explained that. But the section where you have the arrow is always the emitter, and the other one has to be the base, the collector. So you should be able to identify all of them. If you find this transistor there, you find the arrows going away from the emitter, you would already conclude that this is a PNP transistor. Yeah, in a PNP transistor, the flow, the maturity carriers from the emitter are positive. So since it's always moving from the emitter, it's actually moving away from it because it's already positive, like I said. Now, the moment you know it's a PNP transistor, so PNP transistor, so what is in the middle letters N, it means the collector and the base would have to be more negative than the emitter. So it is right here. You can find a negative batteries connected to your collector, and this one is grounded, and this is positive. So in a way, P and P, so negative in the middle, so collector and the base are more negative than the emitter. It's fine. Okay. So next thing you would do now, once you ascertain that your transistor is correctly biased, you would start solving two sides. You always have two sides to a transistor circuit. You have the input side and you have the output side. Okay, so let's solve for the input side. Okay, now how you solve for that? I typically use a method where I start from one point and then you go through here, through the loop, and then you keep writing the different drops you have. Now, whenever you're going along this loop, for example, whenever you're going in the direction of increasing potential or decreasing potential, so you're going to see once you write the current. If you go in the direction of current, we know current always flows from high potential to low potential. Okay, so if I just annotate on this diagram there, it's useful to put the current actually. So if this is the emitter, and you can find the arrow going in here, so this would be the emitter current. So you can write that IE is going to flow like this. Important. And we know that IE is always equal to IB plus IC. Okay, this is your IE. So since IE is going into it here, you would have to have IB going here and IC going here. Yeah, because this is going into it. This will have to split in this way. This is your IB. And this is your IC. It's very important to put the correct direction of current because we will start using them to get the polarity of voltages right. Okay, so let's start for the input side. If you start from here and you start going, so there's no resistor in this part of the base, so there's no voltage drop from here. Now, like we mentioned earlier, remember we said your emitter and base junction is always forward biased. We mentioned that. So if it is forward biased, it means you will have a 0.7 volt drop. We've seen that for silicon. The when your diode is forward biased, you would have a 0.7 drop across your emitter and the base junction because it is forward biased. So since this is positive here, so this potential there is more positive than this one. As you can see, this is grounded, this is positive. It means when I go from this point to this point there, I'm going in the direction of increasing potential. Yep. So this is why here you have a plus 0.7. Okay, plus 0.7. So this is how I'm going to write the equation for the input side. I'm going to write 0.7 plus because I'm going from a low potential to high potential. So I'm going in the direction of increasing potential. Then as you go through this resistor there, just see the direction of current. The current is flowing in this direction. I'm going from here to here. I'm going from a point of low potential to high potential because current is flowing in this direction, as you can see. So this has to get a high potential. So it means when I go from this side to this side, I would have to add, because I'm going in the direction of increasing potential, IE times 20. Yeah, this is Ohm's law. So current times the resistance. I'm not putting any K there, so I'm assuming I is already in milliampere. So again, I start here. There's no drop here because it's just a short circuit. And then you have 0.7 coming in here. And then you add this drop. And then as you go from here to here, you have to minus 10 now because you're going from positive to negative because you have to close the loop. So minus 10 equals to 0. So this is your equation for the input side from which you can find IE.